Maths Boy here, and this is a quick video on linear transformations for A-level further maths. So we'll start with these 3 prior knowledge check questions of matrices that you should have done earlier on in the course. So can you have a go at those, and then I'll give you the solutions. Okay, so for number 1, you should have left one is AB and the right one is BA. For question 2, the determinant is minus 10. And for part B, we've got minus 1 over 10, lots of minus 2, minus 1, minus 4, and 3. For the third one, that should be pretty easy. It should only take about 2 minutes, that one. That's number 3. Okay, so you can use matrices to describe linear transformations. You'll be familiar with transformations from GCSE, i.e. reflections, rotations, translations, and enlargements. A transformation moves all points x, y in a plane according to the same rule. So, the new points are known as the image. For example, I've got S, T, and U here. Find the image of the point 2, 3 under each of these transformations. So you can write the coordinate as a vector, i.e. the directions from 0, 0, and sum in the values. So we should get 6, 2 for the first one. For T, we should be getting 1, 5, and then for U we should be getting the coordinates, substituting in, of 6 minus 4. Okay, that is your basic knowledge of 7a here, exercise 7a if you want to practice this. So, there's another one. So a linear transformation has 2 properties. It only involves linear transformations of x and y, so no powers involved. The origin, 0, 0, is not moved by the transformation, i.e. this one with S only involves linear transformations, so the origin is not moved. For the second one, this only involves linear transformations and the origin is not moved. And the third one, we've got 2y minus x squared. Well, the first one is false because we've got an x squared, so no powers. Is this bit, which is quite important, and we've got a power there, so that must be false. The second one, the origin is not moved. Well, that has to be true. So T here is the only linear transformation in this list. Okay. Moving on. So I've got a linear transformation S, currently represented by the matrix. Since A, B, C, D, pre-multiplied by x, y, is ax plus by, cx plus dy. In a 2 by 1 matrix, find the matrices to represent these linear transformations. TV, well T, write the numbers in the respective positions, so 1, 2, 3, 0. And for the second one, that's just 0, minus 2, 3, 1. Okay, so the square S has coordinates 1, 1, 3, 1. 3, 3, and 1, 3. Find the coordinates of the vertices of the image after the transformation given by the matrix. M, which is minus 1, 2, 2, and 1. Write the coordinates of the vertices as vectors and combine them into a 2 by 4 matrices. So I've got my coordinate matrix. So the information has gone into a box. Now multiply the transformation matrix by the coordinates. So 2 by 2 by 2 by 4, so another 2 by 4. Okay, because remember, those have to be the same. Middle 2, but the outside 2 will tell you what matrix it will be. So multiplying them, each term is multiplied carefully. Carefully multiply each term, and I got the values of 1, minus 135, and 3795 you should get for those. The new vertices will be at 1, 3, minus 17, 3, 9, and 5, 5. That's it. Okay. There's the original ones, and the new ones are translated up there. Okay. So, In this next part of the section, we're going to look at how to represent reflections, rotations, and enlargements using matrices. And now, this is important, but a translation are not linear transformations as the origin would move, so these aren't covered in this section. Okay. To decide what transformation a matrix performs, you should consider its effect on two simple vectors. Okay. So the I and J vectors here, using the identity matrix 1001. So here's a question. Describe fully the geometrical transformation represented by the matrix 3003. This is telling us that if the original coordinates are 1001, new coordinates will be 30 and 03. Ensure they are in the correct order. You should always start with the sketch of 1001 and then mark on the two new coordinates. Nice and simple. So the coordinates have stretched outwards. This matrix is an enlargement of scale factor 3 times 0, 0. And that's it. Next one. Minus 1, 0, 0, minus 1. Okay, so we've got 1, 0, and 0, 1. The new coordinates are minus 1, 0, 0, and minus 1. And also the sketch again of the I and J vectors, and J base unit vectors, and the new ones. So this is not a reflection in y equals x as the coordinates will match up, so be careful here. So we'll have moved 180 degrees around the centre. The transformation is therefore a rotation of 180 degrees about the origin, or 0, 0. Okay, the marks. Okay. So, looking at this one then. 0, minus 1, minus 1, 0. Okay, so we'll start with the I and J base vectors. Pretty explicit this now. And a bit like last time, this is not a reflection in y equals x as coordinates don't match up. However, they've been reflected in a different way, and this time y equals minus x. So this is therefore a reflection in the line y equals minus x. Okay. Hopefully this is very explicit from GCSE. Okay, so the base unit vectors, and pretty explicitly you can find out what they reflect. Okay. So we will now consider these problems in reverse, finding a matrix for a particular transformation. As you have seen, quick sketches are vital when thinking about these problems. So, find a matrix for the transformation reflection in the y-axis. So start with the sketch as normal, and where would they end up? That's the question we want to ask. Well, so the original pair was that, the identity. So the second coordinate hasn't changed, we've got minus 1, 0, 0, 1. Now we want a matrix to form this transformation, and this will let. This is your final solution. Okay. So as you've seen, sketches are vital when thinking about these problems. So find a matrix to represent an enlargement, centre of the origin, and scale factor 2. So the sketch as usual. Once you have sketched, let's go on to the matrix, and you can easily see it's 2002, so this matrix will enlarge the shape by scale factor 2, centre of the origin. That's it. Other one, rotation of 45 degrees anti-clockwise about 0, 0. Okay, so as we know, we want to find where it ends up, so it's going to be somewhere around there. Not necessarily as obvious that this time as to what the new coordinates are. As you look at it in a bit more detail, the new red coordinate will still be a distance of 1 from the origin because there's been no enlargement. 45 degrees, got the hypotenuse, got the opposite and the adjacent sides. I want to be using sine, cosine and tan here. So if I want to be using opposite is sine theta times the hypotenuse. Sine 45 multiplied by 1, which is 1 over root 2. And same for the adjacent as well. That'll be 1 over root 2. So as they are in the diagram in the top right. Okay. Now we can adjust the transformation matrix based on the new coordinates. So the new one would be 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. That's it. And that is the answer. That's it. As a general rule, a matrix representing a rotation of angle theta anti-clockwise about the origin, so it must be anti-clockwise for this to work. It's cosine theta minus sine theta, sine theta, cosine theta. That's it. So there's two definitions that I recommend everyone learns when I teach this, and it's invariant point and invariant line and the difference. So an invariant point, these are points which map onto themselves under a transformation, and an invariant line are lines which map onto themselves under a transformation. Okay, so that must be a line, invariant point is a point. Okay. As we were, find the image T prime of the triangle T with vertices 1, 1, 1, 2, and 2, 2. First thing is to find the image, and the second part is to sketch T and T prime. Part C, describe geometrically the transformation represented by M. This is kind of an exam style sort of question. Multiply by the coordinates, that should be nice and easy now. So we can kind of see what's going on. So the triangle has been stretched by a factor of 3 parallel to the x-axis and a factor of 2 parallel to the y-axis. So this is a quick note that if A equals B and the transformation is an enlargement with scale factor A, okay? So for any of these structures, the x and y axes are invariant lines and the origin is an invariant point. For a stretch parallel to the x-axis only, points on the y-axis are invariant points, and any line parallel to the x-axis is an invariant line. That's the difference. For a stretch parallel to the y-axis only, points on the x-axis are invariant points, and any line parallel to the y-axis is an invariant line. It's important to realise that if the stretch is in both directions, then all of the x and y axes are invariant lines, the individual points on the line are not, which is pretty explicit. So if a linear transformation is represented by matrix M, then the determinant of M represents the scale factor for the change in area. If the determinant is negative, it means that the shape has been reflected. So for example here, for this question, part A is a transformation stretch parallel to the x-axis with scale factor 2, and a stretch parallel to the y-axis with scale factor 4. Part B, the sketch would be quite helpful here. So the area would be 3 square units, well this one in particular, it's 3 times 2 over 2. Part C, the determinant would be 8. Okay, so I'm doing diagonal rows here. So the area of the new triangle will be 24, because it's 3 times 8. 3 times the determinant. So the way to work that out is the area multiplied by the determinant. Okay? A10, B01, and C20 are the vertices of a triangle T. Triangle T is rotated 90 degrees anti-clockwise around the origin, and then the image T prime is reflected in the line y equals x to obtain the triangle T double prime. On separate diagrams, draw T, T prime, and T double prime. So there we go. So rotated 90 degrees about the origin, so I'll move to there. Moving the x points, then T double prime is reflected in the y equals x. So reflecting that will give you that. So that should be part A. Part B. Part 1, find the matrix P such that PT is equal to T prime. And the second one, find the matrix Q such that QT prime is equal to T double prime. So these are asking you what matrix takes you from T to T prime and from T prime to T double prime respectively. So consider coordinate changes for this one. So I always like to look at it as the original pair of and j vectors, and then putting them into their separate coordinates of 0, 1, minus 1, 0, which is coordinate for P. That's that matrix. For Q, the second transformation is a reflection of y equals x. Remember, using the standard starting coordinates of 1, 0, 0, 1. So y equals x, it will transform it so the coordinates just swap around and I get 0, 1, 1, 0, the basic one. And that will be matrix Q. Part C, by finding a matrix product, find a single matrix that will perform a 90 degrees anti-clockwise rotation, followed by a reflection on the line y equals x. So it's important to note that P acts first and then Q acts onto P. So QP is 2 by 2 multiplied by 2 by 2, which will give you 2 by 2 at the end. So multiplying rows and columns, pretty standard stuff now. So multiply that out, and that will give you, I got 1, 0, 0, minus 1. So how those have changed, well, that is more than likely to be true. This is the reflection in the x-axis. So the original diagrams that we had initially, well, there you go. You can see the overall effect is as above, a reflection in the x-axis. And that's it. It's just a complete flip from this one to this one. Just a reflection in the line equals x. Okay. Moving on. So the following matrices represent 3 different transformations. P, 1, 1, 2, 3. Q, 1, 2, 0, 1. And R is 3, 7, minus 1, minus 2. Find the matrix representing the transformation represented by R, followed by Q, followed by P, and give a geometrical interpretation of the transformation. Ensure you get the correct order here, alright? R acts first, which is acted on by P, by Q, which is acted then on P. So it's PQR. Okay? Let's calculate PQ and then we'll multiply it by R. That's the plan. And remember, another option will be to calculate QR multiplied by P as well. Okay? So, got 2 by 2 by 2 by 2, so we'll get a 2 by 2 at the end. So PQ them, elementary row operations, as usual. And we should get out 1327. Multiply it by R then. Got 2 by 2 by 2 by 2, so we get 2 by 2 at the end. Multiplying them out elementary row operations, I'm not going to go through these. It's pretty explicit. And we should get 0, 1, minus 1, 0. Okay. So this is a 90 degrees rotation clockwise around the origin, and that's it. And that is the geometrical interpretation. Okay. Okay, so you can use matrix products to represent combinations of transformations, as we know. Matrix M represents an enlargement with scale factor k, followed by an anti-clockwise rotation through angle theta about the origin. Part A, you want to find the value of k. Part B, you want to find the value of theta. So part A, we can find the area scale factor by calculating the determinant of M. Then we can use it to find the scale factor of enlargement. Well, if the determinant of M is 16, that should be pretty explicit if you do that on your calculator. And square root of 16, which is 4, so the scale factor of enlargement must be 4. Now, that's important, that bit I've highlighted in red there. Okay, so we've got the rotation matrix times its enlargement will give you the overall. So the rotation matrix will be cosine theta minus sine theta, and all that lovely gubbins. The enlargement matrix will be 4004, remembering it's k, then 0, then 0, then k, whereas k is 4 here. So, and that will give me the overall matrix, I get M at the end. The left hand side will give me 4 cosine theta minus 4 sine theta, 4 sine theta, 4 cosine theta. Compare sides, form equations, remember there can be sometimes multiple answers. So we'll get 135 or 225. or I'll get 45 or 135. So the one that forms both of them, and that's common to both, will be that one there and that one there. So it must be the 135. But wait a minute. Yeah, wait a minute. We could also have had the answer -4 above as well. What would have happened if we used that? It is okay to do so? Question mark, question mark? Well, this is it, to be honest. We'll see in a minute if this is true or not. So the transformation represented by the matrix M is A, B, C, D, E, F, G, H, I. Will map 100 to ADG, 010 to BEH, and 001 to CFI using the vectors. So there's the plane x0, x is 0, xz, be like that, y is 0, and the plane xy is the bog standard plane we all know about, but with just a vertical z. Please note, when operating in 3D, sometimes axes are labelled in different ways. For example here, make sure you are reading the right way around. From this way around.
Nightmares creep while you and me repeat. This bittersweet heat is suffocating.
You will see this
I'm waiting and always hesitating. Kryptonite desires set my heart afire.
Three dimensions, then a reflection
Heart on fire.
Part A,
set my heart afire.
Part B, finally on the transformation.
My bones crave your skin. Temptation within. Mistakes ignite the silence. Nightmares creep while you and me repeat. This bittersweet heat is suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire.
Y is 0. I'll just emphasize it a little bit. So the fundamentally you need to know are those three there.
Set my heart afire.
If you want some sudden evil, so you need to learn that. They need to learn. Set my heart on fire. transformation represented by M. This is the pattern that is in the question. Okay, so it's a rotation anti-clockwise around the y-axis. Okay, compare size form equations. Remember there can sometimes be multiple answers to the solutions. So we've got 30 or 330, so using the period of cosine theta is 360. You can make up your own puns for that, what I just said. Or theta can be 30 or 150. So the one that's common is for 30 degrees, so theta must be 30. Part B, you need to multiply that by minus 1, minus 2, 1 straight on your calculator. And you get 1 minus root 3 over 2, minus 2, and 1 plus root 3 over 2. Okay. So that will be the answer to the final question, part B. Okay, so you can use inverse matrices to reverse the effects of a linear transformation. So the triangle T has vertices at A, B, and C. The matrix 4, 3, minus 1, 1 transforms T to the triangle T prime with vertices 4, 3, 4, 10, and minus 4, minus 3. Part A, find the coordinates of the points A, B, and C. So that the coordinates of the original triangle T are given by the matrix X. So the matrix M multiplied by the original coordinates X gives us the new set of coordinates. Okay, so multiply both sides by the M minus 1. Okay, M minus 1 is just the identity and so can be cancelled out. So I get X is equal to M minus 1 of that. So to find the original set of coordinates, we have to multiply the final set of coordinates by the inverse of the matrix that created them. So the determinant of M is AD minus BC, so it'll be 4 times 1 minus 3 times minus 1, which will be 7. Fill in the parts of M minus 1, so we've got M minus 1 is 1 over 7. Swap up the A and D around, so we get 1 and 4. Both signs of B and C will be 1 and minus 3. Okay. Place with M minus 1 and calculate. 2 by 2 by 2 by 3 will give you 2 by 3 out. We get 1/7 flying through. After showing full working. And we get the solutions of 7, 0, 14, 28, minus 7 and 0. Multiply through by 1 over 7 if you want. So you get 1, 0, 2, 4, minus 1, 0. So the original coordinates were 1, 0, 2, 4, and minus 1, 0. Okay. And finally, the matrix A, 2, minus 2, 4, minus 5 represents the transformation T, given that T maps onto point P with coordinates x, y, onto the point P prime with coordinates 6, 10. Part A, find the coordinates of P. Well, the coordinates of P multiply both by the inverse, so A minus 1 of A is just the identity. So we get x, y is A minus 1 of 6, or of 6, 10. You need to multiply the inverse of A by the coordinate. Find the inverse using your calculator. You get 2.5 minus 1, 2 minus 1. Multiply those by 6, 10. The inverse, we get 35 and minus 16. Matrix B represents the transformation U, given that the transformation T followed by the transformation U is equivalent to a reflection in a line y equals x. Find the matrix B. Okay, well, on the base unit vectors, they will switch. So we get 0, 1, 1, 0. So this is a reflection in the line y equals x. Okay, so A followed by B equals the matrix for that. So BA will be that. So multiply both sides by A minus 1. So B is the reflection of the y equals x matrix times the A inverse. Originally A inverse from part A. Multiply the two together to give you matrix B, which would be minus 1, 2.5, minus 1, 2. 2.5 you could have 3 over 2 as well. After all, so as a decimal, it looks a bit neater. And also, it looks horrible if you left it as 3 over 2. But 2.5 looks a bit neater to me. Okay. that is the end of linear transformations. Make sure to like and subscribe to the Math More YouTube channel, of course. And there'll be tons and tons of videos on here for A-level further maths. This is another one because why not? So enjoy, and I shall see you all